Welcome to Analyzing Normal Data. And what's a sigma anyway? In this short video, what we'll take a look at are some of the descriptive statistics used to measure and understand central tendency and variation in normally distributed data, as well as taking a look at how to visually understand and use standard deviation. In this example, I've plotted out some process data, and when I do plot it out as a histogram, it tends to look like a mounded hump or a bell-shaped curve. That's not unusual for most of the business data that you'll be working with. We'll talk later in a separate video about what happens if the data you plot doesn't look like a bell-shaped curve. But in this example, let's assume that we've got normally distributed data, bell-shaped curve data. One of the first questions that I want to know is, what's the central tendency? What should I expect to see the next occurrence be like? Or of all of the data points that have been collected, what is the average? Now, we know from back in most of us, it was grade school math classes, there are three ways to determine central tendency or average for a data set. You've got the mean, median, and mode. To calculate the mean, we take all of the data values, add them all up, divide by the total number. To calculate the median, we take the middlemost data point. So we'll start with our minimum value and our maximum value. We'll toss those out. Then we'll go to the next largest and the next smallest, and we'll work our way to the middlemost data point, the median. And to calculate the mode, we identify the most frequently occurring data point, or if you plot the data out on in a histogram, it's going to be the tallest bar of your histogram. And here's what we know about data that's normally distributed. When you calculate the mean, median, and mode, they're all going to be about the same, and they're going to be located right here in the middle. Our average or central tendency for normally distributed data, mean, median, and mode, are going to be equal, and they're going to be in the middle of our mounded hump. The great thing about all three of these ways to measure central tendency, the great thing about calculating central tendency using mean, median, and mode is that it's a robust way of measuring data. And what I mean by robust is that all of the data in the data set needs to be used to calculate mean, median, and mode. You've got to take all of the data points and add them up, divide by the total number for the mean. You've got to take all of the data points and then work your way to the middlemost data point for the median. You've got to plot out all of your data points and then find the most frequently occurring one for the mode. In all three cases, you use all of your data. It's a robust way of measuring central tendency, all three of the techniques. What most statisticians have agreed upon is that we use the mean most frequently. There are exceptions where we'll use one of the others. The nice thing about normally distributed data, though, is that mean, median, and mode are all going to be the same. But if you hear me say average from this point on, and I don't say mean explicitly, when I say average, I'm going to be meaning mean unless otherwise stated. Let's now take a look at how we measure variation, or the amount of spread in a normally distributed data set. All right, in this example, I've got a normally distributed data set. Looks like a bell-shaped curve. Right down the middle is where our average is. We know that's going to be the mean unless I state otherwise. And the question now becomes, how do I measure the amount of spread or the amount of variation or how fat this bell-shaped curve is? We've looked at other videos and identified that when you're working on process improvement projects, understanding central tendency, very important, but also understanding the amount of variation that you've got in your process is important as well. So how do we determine variation? Well, one simple way is take a look at the minimum data point, compare it to the maximum data point, and that distance between the two, we give it a value. We call it the range. And here's the great thing about range. It's easy to calculate. It's easy to understand. Everybody understands it. But there's a problem with range. Range only relies on the minimum and maximum data point. There's only two data points that are required for you to calculate this value. It does describe spread of the data set, It does give you an indication of variation, but it's not a very robust way, because if there was something unusual that happened to the minimum, or some uncharacteristic phenomena that created an unusually large maximum, the spread would be much greater than what we would typically see in the rest of the data points. We need a more robust way of understanding spread. Range is nice, but range is incomplete. So we're going to take a look at other ways to measure spread. All right, so in this example, I've got another data set. I plotted it out as a histogram. It looks like a bell-shaped curve. One way we can measure variation is by doing our range calculations, but another technique can be used. And what I'm going to do is I'm going to observe on this bell-shaped curve a particular point on this side and on this side, and we're going to give it a name. We're going to call it a saddle point. And here's how you calculate saddle points. A saddle point is where the upside down bowl of your bell-shaped curve meets the sideways bowl of your bell-shaped curve. Where the upside down bowl intersects with the sideways bowl, that's where our saddle points are located. After I've determined where the saddle point is, I'm going to measure that distance from the saddle point to the middle, to the mean. And I'm going to give that value a name. I'm going to call it saddle point distance. It's that distance from the saddle point to the mean. Here's the great thing about saddle point distances. They change depending upon the fatness of our bell-shaped curve. So let me draw another bell-shaped curve. All right, in this next example, I've got a bell-shaped curve. I've drawn my saddle point, and I've measured the distance to the middle. And what I want to do next is I'm going to draw another bell-shaped curve, this one a little bit fatter bell-shaped curve. And again, I'm going to take and identify where the upside down bowl meets the sideways bowl of this curve, and that is right about here. Notice that the saddle point distance is much bigger. Fatter bell-shaped curves, bigger saddle point distance. Skinnier bell-shaped curves, smaller saddle point distance. And here's the great thing about saddle point distance. It's a robust measure of spread. Unlike range, which only requires 2 data points to determine and calculate, where you take a look at the minimum and the maximum data point, range is not a very robust measure of spread. Saddle point distances are. The only way that you get a saddle point distance is you have to take all of your data and plot it out as a bell-shaped curve. And then when you see where the upside down bowl meets the sideways bowls, you can measure that distance. You have to have all your data to calculate saddle point distances. Saddle point distance is a robust measure of spread. All right, in this next example, I've got 2 data sets, the 3, 2, 1. All right, in this next example, I've got 2 data sets. Let's call the black line, the black histogram, the black bell-shaped curve our current state data. And when I measure out the saddle point distance from where the saddle point is to the mean, I get a value of 3. Just an arbitrary number. It could be 30, it could be 50. I'm just going to say it's about 3 units away. We now then take a look at the future state data. It grabbed all the data, we plotted it out as a histogram. When it was plotted out as a histogram, it looked like the blue bell-shaped curve that we see right here. And its distance is about 1. The great thing about saddle point distance is that to calculate it, there's no formula involved. All you have to do is plot your data out as a histogram where the upside down bowl meets the sideways bowl. That's where your saddle point is, right here. And then you measure that distance to the mean. Bigger saddle point distances mean you've got fatter bell-shaped curves. Smaller saddle point distances, smaller numbers for your saddle point distance means that you've got skinnier bell-shaped curves. Saddle point distances that are small mean there's less variation. Saddle point distances that are large mean there's lots of variation. If it might not be current state and future state that I'm looking at. We could say that the black line represents the Chicago branch and its performance, and the blue line represents the Los Angeles branch and its performance. What I could say from this is that they both have the same central tendency, they both have the same average, but the LA branch has much less variation in the performance that we're observing here. All right, in this next example, we plotted out our data. It looks like a bell-shaped curve. When we take a look at where the upside down bowl meets the sideways bowl of our data set, we know that's where our saddle point is, and we've measured that distance. We've got saddle point distance. Saddle point distance is a robust measure of spread. It's using the entire data set to calculate it. But that's hard to say, saddle point distance. So here's what statisticians do. We use acronyms and we use jargon terms. We could have called saddle point distance saddle point distance, SPD. But that's too easy. Anybody could crack that code. Let's give it a different acronym. Let's call it SD. That's too easy as well. Here's what we did. We took this distance from the saddle point to the mean and we measured it. And we gave it an acronym, but we used a letter from a language that few people speak, the Greek language, and an alphabet that isn't the same as your standard English alphabet. And we gave that saddle point distance the Greek letter sigma as a representation. When you're dealing with population data and you're measuring the upside down bowl meets the sideways bowl and the distance to the middle to the mean, that saddle point distance is called sigma. Sigma is just a measure of spread. It's a measure of how much fatness do we have in our data set. A small value for sigma means there's very little variation. A large value for sigma means there's much more variation. The problem with sigma is that it's difficult to type on a standard English keyboard, so we needed another way to describe this term, this variable. We strung together two words that all by themselves make perfect sense to any person that hears the words, but when stuck together mean much less sense. Sigma, or that Greek letter, sigma, is also equal to the term. Standard deviation is also what this value is. And then we gave it the kiss of death by stating that in order to calculate standard deviation, instead of plotting out your data as a bell-shaped curve and then taking a look at where the upside down bowl meets the sideways bowl and measuring that distance to the middle, instead of calculating standard deviation in that simple visual manner, we said in order to calculate standard deviation, you're going to have to use this formula to calculate standard deviation. You can highlight the data in Excel and use the standard deviation formula calculation, or you can manually stick each of your data points through this particular formula. Standard deviation is equal to sigma. Sigma is equal to your saddle point distance. Saddle point distance is easily calculated by just plotting your data out as a bell-shaped curve, and where the upside down bowl meets the sideways bowl and measuring that distance to the middle. There's your saddle point distance, there's your sigma, there's your standard deviation. And it's a way to measure spread, the amount of variation in your data set, how fat your bell-shaped curve is. We've got now robust measures for central tendency, mean, median, and mode. We've also now got robust measures for spread, standard deviation.